There has been a nuclear accident in the Soviet Union and
An official announcement from the Council of Ministers. There has been an accident at the Chernobyl atomic power station. One of the atomic reactors was damaged.
That Soviet nuclear accident in the Ukraine created fallout today in Chicago.
On April 26, 1986, fourth reactor of Chernobyl nuclear power plant located in then Soviet Union, now Ukraine, exploded. This released a massive amount of radioactive material into the atmosphere. This incident, still regarded as the world's worst nuclear power accident, changed the lives of millions of people, devastated the environment, and left scars on nations beyond the disaster's origin, including countries like Sweden and Belarus. But what really happened that night? How did a simple test lead into world's one of the worst nuclear power accident? This video covers the entire story, including the disaster's long-term and immediate consequences, and most importantly, what can we learn from this case study. So without wasting any time, let's get started. Chernobyl power plant produces electricity using nuclear energy through the process of nuclear fission. Nuclear fission is the process whereby nucleus of heavy atoms like uranium-235 are broken in two fragments. This releases a lot of energy. This energy is converted into steam. Steam rotates the turbine which is connected to generator, and generator converts kinetic to electrical energy. But the question here lies, why is energy released in this process, and why are only atoms like uranium-235 used? To understand this, let us clarify the difference between a stable and unstable atom. An atom is made of electrons, protons and neutrons. The protons and neutrons are tightly packed inside the nucleus, while the electrons move around the nucleus in orbits. Inside the nucleus, two forces act. First is the electromagnetic force, which causes protons to repel against each other since they have the same positive charge. The second is the nuclear force. This is a much stronger force which holds the protons and neutrons together to keep the nucleus stable. For an atom to stay stable, the number of protons and neutrons in the nucleus must be balanced. Protons are positively charged and the neutrons are neutral. But if there are too many protons compared to neutrons, the electromagnetic force becomes much stronger than the nuclear force. This imbalance causes the protons to push away each other, making the atom unstable. For example, carbon's famous isotope carbon-12 has 6 protons and 6 neutrons inside the nucleus. Having balanced number of protons and neutrons inside the nucleus makes very stable. However, uranium-235 has 92 protons and 143 neutrons. Even though the number of neutrons are higher, they cannot balance the electromagnetic energy created by 92 protons. Hence, this makes the uranium-235 very unstable. However, uranium-235 cannot work on its own. This atom needs an help from outside to trigger the nuclear fission. In our case, we use neutron to trigger this help. So neutron collides with uranium-235 to create uranium-236. Uranium-236 is much more unstable than uranium-235, and to stabilize itself, it will be splitted in two parts, releasing a lot of energy in this process. Once this is very clear to you, now let us understand why splitting of uranium releases so much energy. In order to understand the reason behind energy release, let us keep one thing in mind. An atom's mass comprises of neutron, proton, electron and the binding energy. This binding energy keeps electrons and protons inside the nucleus together. Now uranium-heavy atoms like uranium-235 require a lot of binding energy to hold protons and electrons together. However, once the splitting has occurred, less binding energy is required as the fragments have divided in size. Now this excess energy, which is no longer required, is released in the form of heat. Let us understand this with an example. Uranium-235 has a mass of 100 gram. Now the neutron that is going to collide with uranium-235 is weighing around 10 gram. So the total weight of before splitting will be around 110 gram. Uranium-236 will be weighing around 110 gram. After splitting, the total weight of the two fragments will be around 109 gram. So this 1 gram of excess mass that is no longer needed will be released in the form of heat. This is the reason behind why nuclear fission releases a lot of energy. Another thing to note here is that when the nucleus splits, not all the neutrons and protons will be equally divided. some of the neutrons will be left over, and these leftover neutrons won't just disappear, rather they will collide with the nucleus of another uranium-235 atom. And like this reaction will go on and on. This chain reaction in nuclear fission is very powerful. Once the reaction starts, it produces lot of energy very rapidly. If this fundamental understanding is clear to you, let me simplify how a nuclear plant works so that you will be able to understand the incident at a much deeper level.
So the main components of a nuclear plant include a reactor, steam generator, turbine, generator, condenser, and a cooling tower. Inside the reactor is a reactor vessel where all the reactions take place. The reactor vessel contains control rods and fuel rods. Fuel rods are the fuel source of this entire reaction process. They store uranium-235. Control rods are made of materials like boron and cadmium. These materials absorb neutron during the reaction, slowing down the entire reaction process. So when the control rods are inserted inside the vessel, they absorb neutrons, slowing down the process. In order to initiate the process, firstly the control rods are removed and materials like polonium and beryllium are inserted inside the vessel. These materials react to produce neutron which collides with uranium-235 to produce uranium-236. This is then split in two fragments, releasing a lot of energy. This energy increases the temperature of the water that is inside the reactor vessel. This water then moves to steam generator. From the steam generator, steam moves to turbine, which is then connected to a generator which converts kinetic to electrical energy. From the turbine, the steam is also sent to a condenser where it is converted again into water. The temperature of water is again cooled down by sending it to cooling tower.
At the Chernobyl power plant, all the reactors were connected to 3 backup generators. These backup generators ensure that enough power is supplied during power failure so that the entire plant is prevented from shutting down. However, these backup generators took around 60 to 75 seconds in order to start. This means that the entire plant can shut down for this much duration. Essential components like coolant pumps cannot stop functioning as they supply cold water to the reactor vessel. If the cold water is not supplied, excess heat inside the vessel might generate, which can cause sudden increase in the pressure. This rise in pressure can have disastrous consequences. So on April 26, 1986, engineers wanted to test if they can supply enough power for these 60 to 75 seconds so that the coolant pumps keep on functioning. And for their plan was very simple: to reduce the power output of the reactor to 700 megawatts and to see if the turbines can supply power to the coolant pumps. So when they proceeded as per their plan, they overlooked a very crucial detail. Whenever nuclear fission occurs, iodine is also produced. This iodine decays into xenon-135. Now xenon-135 absorbs neutrons during this process and slows down the entire nuclear chain reaction. Now, in order to prevent this decay of iodine into xenon, neutrons must collide and stick with iodine so that this decay is prevented. However, when they reduced the power to 700 megawatt, lesser neutrons were available to stick with iodine. This meant that more iodine was decayed into xenon-135, and xenon-135 further absorbed more neutrons, slowing down the entire nuclear reaction. This led to creation of a vicious cycle known as xenon poisoning, and this reduced the power output to as low as 30 megawatts. Now, in order to increase the power output, operators started to pull out control rods. Slowly and gradually, they were able to reach 200 megawatts, but this was still lesser than 700 megawatt. And in order to reach there, they pulled out more rods, leaving only 8 rods inside the vessel. Now, these violated a safety rule which indicated that there should be 15 rods inside the reactor vessel at any time. Now, since only 8 rods were present inside the vessel, this created a massive power spike. This power spike converted the water into steam at a rapid rate. Now, the reactor was designed with a positive coefficient of reactivity, which meant that the steam will further intensify the reaction. Slowly and gradually, the reactor became unstable. To control things, operators initiated emergency shutdown, which meant that the control rods will be inserted inside the reactor vessel and the reaction will be completely shut down. However, things went the other way when they initiated the emergency shutdown. The tip of the control rod was made of graphite. Now, graphite is a very good moderator. Usually, whenever nuclear fission occurs and neutrons are released, neutrons have a lot of energy and they move very rapidly. Their movement needs to be slowed down. Slowing down is caused by moderator, which then increases the efficiency of the overall reaction. So the tip of their control rod acted as a moderator and increased the efficiency of the reaction. Slowly and gradually, the pressure spike caused the explosion of a 1,000-ton reactor roof, followed by another blast within just couple of seconds. The Chernobyl disaster had a devastating short-term and long-term impact. Around 2 workers died in the explosion, while many others suffered from acute radiation syndrome. Around 30,000 people of Pripyat were evacuated to safe zone so that they are not exposed to high radiation. A 30-kilometer wide exclusion zone was prepared around the plant to prevent people from getting exposed to radiation. People, especially children, in the following years were diagnosed with thyroid cancer. The disaster caused economic loss of around 235 billion. Radioactive particles from the explosion were spread into countries like Sweden, Belarus, and even parts of Canada. From the entire case study, I have derived 3 main learnings. The first one is that an atom's stability depends on how protons and neutrons are arranged and how electromagnetic forces and nuclear forces balance each other. If these forces are unbalanced, atom becomes unstable. Secondly, the reactor's power output must be very closely monitored. If this is not done, xenon poisoning might occur, which can further reduce the power, making things worse. Lastly, yet importantly, while control rods are meant to slow down the reaction, their graphite tips can have the opposite effect. Graphite acts as a very good moderator, slowing down the neutrons and increasing the efficiency of fusion reactions. That's all from my end for this video. If you found any value in the video, please like, subscribe and share. I'll see you in the next video. Bye bye.